Hello there, AP Environmental Science class. Welcome to part one of my lecture on chapter two, Science, Matter, Energy, and Systems. So once again, this is going to be kind of a review type of chapter. It's going to talk a lot of different things, okay, as we go through this chapter, basically talking about science, the scientific method. We will review matter, atoms, how they come together, protons, neutrons, electrons, those types of things. Then we'll go into types of energy, and then again the systems on Earth here that kind of use the science, the matter, and the energy. So that's kind of where we're headed in this chapter. Once again, I will break the chapter up into two parts. There are 47 slides, so you're looking about 24, 25 or so slides per lesson here. Okay, per part. All right. So again, part one. Here we go. All right. Starts off with a core case study. How do scientists learn about nature? Well, basically, they do experiments in the forest. So one is the Hubbard Brook Experimental Forest in New Hampshire. This is a forest that has actually been set aside to be able to do scientific experiments on it. And one of the experiments they did was to compare the loss of water and nutrients from an uncut forest to one that has been stripped. And again, that was the control site versus the experimental site. What it found was that the strip site, if you basically cut down trees, you're unfortunately producing more runoff, 30 to 40% more runoff. And we'll talk about in a couple of chapters how sediment runoff is actually one of the major pollutants of our rivers, believe it or not. So it doesn't necessarily have to be toxic stuff that is pollution. Runoff of sediment is considered pollution as well. And when you strip a forest, when you cut down trees, when you take away plants, you lead to soil erosion and you lead to more runoff, which is what this experiment proved. Well, it also proved that there was more dissolved nutrients in the strip site, and again, more of that soil erosion. So that's kind of what this chapter, at least the first part of this chapter, is going to talk about. A little bit about the scientific method. Again, here's just a picture here. The left side was the control. The right side was the experiment. Again, where the forest was stripped. And again, once again, on the experimental side, much more in the way of runoff, much more in the way of erosion. So what do scientists do? Well, scientists collect data, develop theories, models, and laws about how nature works. So what are the tools of scientists? Again, I think you guys know this: observations, measurements, and experimentation. So, what do we do? How do scientists collect evidence and actually use it? Well, we have the steps in the scientific method. And again, a lot of this is going to be review for you guys. So what's the first step? Identify a problem. Then you're going to find out what is known about the problem. That's kind of the background information, right? Then you're going to ask a question, right? That's your testable question right there. Perform an experiment, collect data, analyze data to answer the question, and then you're going to propose a hypothesis to explain the data, and then you may actually go do your experiment again to either prove or disprove your hypothesis even more, right? So you use the hypothesis to make testable projections, then you form an experiment or perform an experiment to test those projections, and then of course you accept or revise the hypothesis. If you revise it, you kind of go back and do some more tests, some more experimentation. If the hypothesis is proven to be accurate, then you're pretty much done. Then you develop a model, right? Another way to study nature, right? What is a model? Well, it's some way to take something big and turn it into something smaller that you could deal with maybe in a classroom or in a textbook or something like that. And then we have scientific theory, right? If you kind of go through all this and it sounds pretty good, theory shows up, which is a well-tested and widely accepted hypothesis. So this is kind of the scientific method, kind of from beginning to end here. Again, kind of just what we talked about. I'll be honest with you guys. I kind of said it in chapter one. The little graphs and the visuals that are in this book, in these notes, are actually very good. They're very concise, very succinct. So my advice to you is take a look a lot at these visuals and understand them, right? Because again, here lays out basically the scientific method right in front of you from beginning to end. All right, so Scientists, one of the key to being a scientist is that you have to be curious and skeptical about everything, and you need to demand evidence. So scientific knowledge advances through scientists publishing details of methods and results, and then peers review those methods and results and either agree with them or refute them themselves. Then new data and analysis can lead to a revised hypothesis, again, if that happens. So what do you got to do? You got to think critically and creativity, right? You have to be able to create things, or you have to have creativity, and you need to think critically in science. So have a skeptical outlook, evaluate evidence and hypotheses using inputs from a variety of reliable sources, and then identify and evaluate personal assumptions, biases, and beliefs to distinguish facts and opinions before coming to a conclusion. Unfortunately, all of us have our bias. So when it comes to science, you kind of have to put that bias aside and kind of look just at the facts. Again, imagination, creativity, intuition, also vital to being a scientist. So, scientific theory, just a couple of terms. This is a widely tested and supported theory by evidence. If it becomes a scientific law or a law of nature, that's just a well-tested, widely accepted description of what's happening repeatedly over and over again the same way in nature. So I would argue a scientific theory kind of here, and a scientific law or a law of nature would be a bit above a scientific theory, meaning we're pretty darn sure that the law is accurate because we see it going on over and over and over and over again somewhere in nature. So science can be reliable, unreliable, and tentative. And if I was doing this lecture 30 years ago, most science was reliable back then. Unfortunately, nowadays, with all the access everyone has to social media and to all these different websites, you really, as a scientist, need to make sure that you're using reliable data. So what is reliable science data? Well, it's data, hypotheses, models, theories, and laws that are widely accepted by experts. They've been through peer reviews. That's what reliable science would be. Unreliable science are results presented as reliable, but without peer review, or maybe they've been discredited. Tentative science is preliminary scientific results without adequate testing and peer reviews, right? So tentative science, probably the worst. Unreliable science, kind of in the middle. And obviously what we want to get to is reliable science, which again has these data and hypothesis and models that have been tested, that have been peer reviewed over and over again, and have proven, at least with all that, to be accurate. The unreliable science doesn't necessarily have the peer reviews, and then again, tentative science really doesn't have peer reviews or any type of adequate testing, hypotheses, things like that. All right, so especially nowadays, guys, as you go through in the internet, as you go through your social media and you see people talking about science, you have to use your best judgment. But again, make sure that you're dealing with reliable science and not unreliable or tentative science. Now, science does have its limitations. Scientists cannot prove or disprove anything absolutely, right? Science attempts to establish a high probability that a theory or a law is accurate. But again, in the end, always something can come up that could mess with those uh, with that answer, right? Or what we think might be a theory or a law. So something to think about. Scientists, again, are not free of their own biases, and therefore hypotheses and results could be skewed towards a scientist's own bias. So again, you have to make sure that you're free of that. And then systems in the natural world involve many variables and complex interactions that mathematical models and statistical tools that can help deal with these. But also, at the end of the day, the systems are so complex that even the high-powered computers we have still could make it difficult to find an accurate result. I'll bring up my former life as a weatherman, right? Meteorologists use computer models to try to forecast the weather, but the weather there's so many variables. Think about the atmosphere. The atmosphere goes from here on the surface, right, up, miles and miles into the sky. It's very difficult to grab all the different variables that are going on at each layer of the atmosphere and put it into a computer model and then see what the results of that computer model are. So that's why meteorologists have a hard time making accurate weather forecasts, let's say out 1, 2, 3, 4, 5 days, because there's just so many variables involved in the atmosphere. It's very difficult to get all those variables into a computer model. Now, as our computers get faster and faster and faster, you can put more and more and more variables into them. So we are getting better results in the meteorological world, right? Predicting the weather compared to, let's say, 30, 40 years ago, but still definitely has some limitations to it. So something to think about. Okay, so that was kind of the first section of the chapter talking about scientists, what scientists do, about the scientific method. Now we're going to start moving into a little bit more of that matter part, right? Science, matter, energy, and systems is the title of chapter 2. So we just did science. Now we're going into that matter part. So what is matter and what happens when it undergoes change? Well, matter has mass and takes up space, right? Matter exists in 3 physical states. I know you guys know this: solid, liquid, or a gas here on planet Earth. And 2 chemical forms, elements and compounds. What is an element? Again, guys should know this, have unique properties, and they cannot be broken down chemically into other substances, right? So your element is kind of your base there. It's basically unique, and you can't break it down anymore. Okay? Known elements are arranged in a chart called the periodic table of the elements. A compound is just 2 or more different elements held together in fixed proportions. All right, that's what a compound is. So element is your base, and then you take elements, put them together to produce these compounds. So for instance, this is gold and mercury. Obviously, these are elements. All right, gold and mercury. You cannot break them down any further than what they look like now. This is their base. Mercury, gold. You can't break them down anymore. Again, but you can combine them with other elements to produce compounds. So elements and compounds are made of atoms, molecules, and ions. As you know, the atomic theory states that all elements are made of atoms. So again, there is a theory that has been tested over and over again. So we're pretty positive that all elements are made of atoms, and that's why we call it a theory. There are some subatomic particles, okay, in your atom, right? You have the nucleus of the atom. In the nucleus, you have protons, which are positively charged subatomic particles, and you have neutrons, which have no charge. And then around, you have these negatively charged electrons, which kind of orbit the nucleus, even though now we're thinking they're really not in like orbits, they're more in like a cloud. Could be anywhere in that cloud of electrons that basically orbits that nucleus. So this is what it looks like, right? You have 6 protons, 6 neutrons in the nucleus, and there are your 6 electrons kind of in that kind of haze, again, around, orbiting around the nucleus here. This is obviously the element carbon, which has 6 protons and 6 electrons. Okay, so what does that mean? That is what I just gave you was that element's atomic number, right? So carbon's atomic number is 6. Hydrogen's atomic number is 1, right? Helium's atomic number is 2. So basically, each element has that unique number, and that's basically the number of protons and electrons in that element, right? So same as number of protons in the nucleus. The mass number is the number of protons plus the number of neutrons in the nucleus, and that could change. So while if the number of protons change, you have a new element. If the number of neutrons change, you don't have a new element, but you have a new isotope of that element. What is an isotope? Form of an element with the same atomic number, okay, same number of protons, but different mass numbers, so have different number of neutrons in the nucleus. A molecule, what is that? Again, I know many of you know this, just kind of going through it. A combination of 2 or more atoms of the same or different elements held together by some form of chemical bond. So we have ions, atom or group of atoms with a net positive or negative electric charge. This is formed when an electron is gained or lost in that atom. So again, you don't necessarily have to have the same amount of electrons and protons. Proton, that's the number, that's the atomic number that determines the element. But again, the electrons, while they're usually the same as the proton, you can lose or gain an electron, and that would, of course, cause and form an ion, which again has a net positive or negative electric charge. Acidity is the measure of the comparative amounts of hydrogen atoms plus and hydroxide atoms, which is a negatively charged there, in a volume of water solution. You guys know this. It's called pH. Neutral is 7. More acidic, you have a pH less than 7. More basic, you have a pH greater than 7. This was just a look at... this was just nitrate loss. Nitrate is a compound. And this was just, again, just kind of more results of that experiment we started the chapter with about the forest in New Hampshire there. All right. Again, just showing how much of that nitrate was lost right in the disturbed watershed, or at least how much was actually increased and then lost. So we lost it, then we increased that nitrate, and then it ended up going down again in that disturbed experimental watershed. So again, just some information kind of going with that previous case study. And then again, here's just one of these great charts that kind of shows you the pH of some certain materials that you may know. So for instance, oven cleaner is very, very basic, looking like a 13 pH, while something like lemon juice and some acid rain, very acidic, has a pH of 2. And then you can see going from 0 to 14 there, acidic to basic. So again, just a chart for you. You definitely don't have to memorize any of this chart. So we use then chemical formulas to help us determine these types of elements and compounds, right? So the chemical formula shows the number of each type of atom or ion in a compound. There are 2 types of compounds: ionic compounds like salt, sodium chloride. This tends to dissolve in water and break into those ions, the positive and the negative charge, and that helps hold that compound together. Then you have covalent compounds like water, H2O, which you have more of a sharing of electrons between different atoms. So this is just a picture of salt, NaCl. Again, oppositely charged particles held together by a strong force of attraction, right? Positive and negative charges coming together to hold together. And then this is just an example of some chemical formulas of covalent compounds, where again, not necessarily a chemical charge, but you have these elements and these atoms that are sharing electrons among one another, and that helps keep them together in some form of compound. All right, so that will conclude part 1 of my lecture on chapter 2, Science, Matter, Energy, and Systems. Make sure to watch part 2 of chapter 2 as well. And as always, thanks for listening.